Hi everyone, Dankman here. Today we're going to introduce this topic, brand new section 5.3, and it's called Factoring Quadratics. You'll remember hopefully from the introductory video that what makes the expressions and equations that we look at in this chapter special are that they involve this x being raised to the second power. And that is what makes them quadratic. Quad going back, I think, to like Latin and meaning the squaring. Okay? And that's where we get quad and the French and Spanish words quad for four, four-sided figure, even four-sided figure square. I believe. You can look me up on that. And so this factoring process is what we've been working on introducing this week, and today we're going to introduce this factoring of quadratics. And so ultimately the question that's raised is, can we factor this expression? So can we turn this expression, which right now is an addition problem of 1, 2, 3 pieces that are adding up together, can we somehow break it down into a multiplication problem of just 2 pieces or 3 pieces? In this case, it's actually going to be 2 pieces, and it's going to basically look like this. Can we figure out how to turn this expression into a multiplication problem of a group times a group? So to make that make some more sense, I'm going to go back here and review that we started by multiplying together a number, for instance, by a group using the distributive property. And then this week we introduced the idea that we could undistribute, so to speak, and turn this addition problem backwards into a multiplication problem. And so we're going to see if we can somehow undistribute a slightly more complicated multiplication problem. And that's the topic today. And this skill is a cool skill, and it goes all the way back to something we've been doing all year, which is we've been looking at these X games, okay, where we've been asking ourselves, for instance, hey, are there 2 numbers we can find that multiply, for instance, to 28 and add to 11? So we need 1 number, 2 numbers that have a sum of 11, add up to 11, and a product of 28, multiply to 28. And you're going to see that come up today when we get to our final problem. So it's a pretty cool topic. I'm excited to introduce it. So let's begin with some review. To multiply, let's recall that when we multiply 3 by the group x plus 4, okay, we're not multiplying the 3 by the x or by the 4, not by themselves anyway, but the 3 times the whole group x plus 4. And for me, I really liked to look at this in a model, a picture. That is a terrible drawing. A picture of a rectangle. And I would think of this rectangle as having a height of 3 units, okay? And then the other dimension across would be a length or width. So let's say height of 3 units and width across of x, and then another 4 units. So that's x and then plus another 4, so the total distance across is x plus 4. So the area of this entire compound rectangle, which is 3 tall by x plus 4 across, would be the height times the length across. So this would represent the area of the whole rectangle. But we could also write the area of the rectangle by taking the first rectangle on the left, which is 3 units tall and x units across, multiplying that to get 3x. And then looking at the second rectangle here, which is 3 units tall and 4 units across, and multiplying that 3 by 4 to get 12 units, and saying, okay, I'll get 3 times x, which is the distributive property, 3 by x, and then 3 times 4, distribute the 3 to the 4, and then I'll add those together, and in that way I get the total 3x plus 12. So I found a way to distribute the 3 and change this multiplication problem, this product, into an addition problem with 1, 2 chunks adding together. So we go from product here in orange, product, to sum. Okay? Now, this week we introduced this idea of starting with the sum. And we want to go backwards from the sum. We want to figure out how to go backwards from the sum to the product. In other words, we want to go from adding things together to rewriting it as a multiplication problem, and the two things that multiply together, the 3-piece and the group x plus 4, are called factors. So we're going to split the sum back up into two factors that multiply together. So the process of reversing a sum backwards into a product is called factoring. Again, I'll draw myself a picture. And this is what that handout was all about, was looking at a rectangle and saying, okay, if I've got a compound rectangle, one piece is 2x, and the other piece is 12, and the question I have for myself is, what can I put in for the height, and what are the two pieces together across going to look like? And so I have to look for a common factor that's inside both the 2x and the 12, and figure out what that height would be, so a number that multiplies both by 2x and by 12. A number that multiplies to create 2x and a number that multiplies to create 12, and then factor that number out or undistribute something, okay? So I'm basically going to try and have an empty slot here at the beginning and fill that in, and then an empty group right here. And I need to figure out what goes inside the two empty parts. And here I can see the number 2 hidden, not very well hidden, inside of 2x, and the number 2 hidden inside of 12. So I can think of 2x as 2 times x, and I can think of 12 as 2 times 6, and I can undistribute that 2, so that'll become the factor out in front of the group, and that would leave behind for me x and 6. So if I write down x and 6 across, then I get 2 times the group x plus 6. And I've factored out 2 and reversed this sum backwards into a product of 2 pieces. So that was called factoring. And this number 2 had a name, okay? And its name was a greatest common factor, because it's the biggest multiplying piece that's inside both 2x and 12. The number 2 is shared between those two pieces, 2x and 12, and it's the biggest thing that's shared between both of them. And so hopefully, in the practice of all week, you've gotten good at factoring out a greatest common factor. Now, as a little reminder, we don't just multiply a number or a single term by a whole group. We also learned how to multiply two groups by each other. Okay, so taking a look at this process, one way to represent that was to draw an entire compound rectangle with 4 smaller pieces. One side could be x plus 3, the other side could be x plus 4, and then we had to basically distribute this x times x, and then we would put that down, and then distribute again. So this, let me back up and review carefully. This entire rectangle is made up of 4 different rectangles. We're going to multiply x plus 3, the height, times x plus 4, the width across. To do that, I'm going to start with this top left piece, x plus 3, and I'm going to distribute x, find this first rectangle, x times x, find the second rectangle's area, which is x tall and 4 across, so that's going to be x times 4. Okay, and that means distributing the x term times x, and then distributing the x term times 4 looks like distributing the x term times 4 over here in the expression, and adding that piece of area on. Then I'm going to move to the 3 term, shown here in the rectangle and shown up here in the expression, and I'm going to distribute this 3 term, so I've got a 3 tall and x across rectangle, so 3 by x. And in the expression, that looks like distributing the 3 times x, and then we'll add that component on. And then our last component, we're going to find this last missing piece, which is 3 units tall and 4 units across. So I'll get 3 by 4. And in the expression, that's distributing the number 3 times the number 4. Okay, this is all review. And now I've got to clean up everything. So I'm going to look at the area of this thing is x plus 3 times x plus 4. So as a product over here, it's x plus 3 times x plus 4. And what I'm doing is I'm turning it into a sum. over here. So I'm multiplying the product out into a sum. So I'm going to take this, which is ugly to look at, x times x plus x times 4 plus 3 times x plus 3 times 4. That's a lot, and I'm going to clean it up. So x by x is x squared. That's the quadratic part. I've got x times 4, which is 4x, and I've got 3x, and I've got 3 times 4, which is 12. And I want you to notice now, and we've done this so many times, in the middle we've got like terms. We've got 4x and 3x, and we're going to combine those like terms, adding 4 plus 3 together. And on the end, I've got a constant term, a number, which came from 3 times 4, giving us 12. So in the middle, we'll have something that comes from adding 3 plus 4, and on the end, we have something that comes from multiplying 3 times 4. Okay? So x squared in the middle, when you add these like terms, 3x and 4x, you get 7x, and on the end we've got 3 times 4, which is 12. Again, we've got an interesting pattern involving a product and a sum. The sum is 3x plus 4x, and 3 plus 4 gives us 7, and the product is 3 times 4. 3 times 4 gives us 12, and it's just cool. It's so cool to me that as we turn products into sums, or backwards turn sums backwards into products, the pattern when we make these quadratics by multiplying together groups, the pattern involves sum and product. And so, if we're looking at the process of multiplying a product into a sum, we've got 3 and 4, and when we go multiplying x plus 3 times x plus 4, we get out this quadratic expression that follows a really specific pattern. It's got the x squared in the front, okay? Then it's got a 7x term, and then a no x at all, just a constant term. So we've got a second power, a first power, and then no x power at all, a 0 power. And so this is the pattern. And the pattern's even more specific, which is that the x squared is sitting there with a coefficient of 1, so there's nothing out in front of that x multiplying that we can see. And so we could say the coefficient of that x is 1. Okay? And then the coefficient of this, the coefficient of x squared is 1. Okay? The coefficient of this x is the number 7. Okay? And since this third piece, or third term, has no variable in it at all, it's got no coefficient, but it's the number 12. So our patterns involve the number 1 in front, and then the number 7 is the coefficient to the x term, and then the constant or numerical term is the number 12. And so, recognizing that pattern, we're going to have to think now about how to reverse this sum backwards into the product that it started as. And that's what this question down here is. If I started you off with this thing, x squared plus 11x plus 28, maybe I could draw myself a picture of it as a rectangle, and I know I'm going to say to you guys, it's going to follow this pattern of having these two groups, so I'm going to subdivide my rectangle here into 4 little sub-boxes, and then I'm going to say to myself, okay, I know the pattern involves having the x squared, and that's going to be my top left piece here. So that's going to give me my x times x. And I know the pattern involves my two numbers multiplying in the bottom right, 3 times 4 to make the bottom right. So it's something times something to make my bottom right of 28. Okay. And then these two diagonal boxes here, we don't know what's in each one, but when we add 3x and 4x together up here, we get 7x in the middle. So here we're going to add these two diagonal boxes together to get 11x. We don't know exactly what's in them, but the numbers here are going to have to work out to make 11x. So let's look at this. So the top left box is x by x, so I know it's going to be x times x. Okay? And that means this box here is going to be something times x, because this box here is x units tall and something across, okay? And this bottom one down here is x units across, and so it's going to be something tall. We don't know how tall it is, but it's going to be however tall it is times x. And so we have to figure out what I'm going to call the red and the blue number, okay? And this is where our x game comes back in. Okay? I'm going to show you that right now. All right? So we've got the red and the blue number. We know those are going to be coefficients here, and when you add the red number together plus the blue number, just like 3x and 4x together sum to make 7x, when we add the red number and the blue number together, we're going to get a total of 11. So the sum is going to be 11, two numbers that are going to add together to make 11. And then also we're going to multiply the blue number times the red number down here to get 28. So their sum is 11 in the bottom of the x, add, and then their product in the top, when you multiply the two numbers together, will be 28. And so we just have to think of two numbers that multiply together to make 28 and add together to make 11, okay? And I happen to know that my two numbers are going to be 7 and 4, okay? Because 7 times 4 makes 28, and 7 plus 4 makes 11, okay? So, what that means is we're going to go back up here, and we're going to say, okay, let's make the blue number 4, and let's make the red number 7, and that means this rectangle is x plus 4 tall, so one of our factors will be x plus 4 units, and then across it's x plus 7, so the other factor will be x plus 7, and what we've done is we've taken this sum, x plus 11, x squared plus 11x plus 28, and we've turned it into a product of two factors. We've factored this thing. We've turned it backwards into a multiplication problem. And just to prove it to you, with me really briefly, if I multiply x plus 4 the group times x plus 7 the group, let's confirm or verify that we get out x squared plus 11x plus 28. So that's x times x plus x times 7 plus 4x plus 4 times 7. So in the front I get x squared plus 7x plus 4x plus 28. And the two middle terms are alike. So that's x squared plus 11x plus 28. So if you want to take this sum, x squared plus 11x plus 28, and factor it into a product of two pieces, we have found the key to that. And the key to that is going to involve this concept of an x game and our compound rectangle, and thinking of two numbers that added up to 11 and multiplied to 28. And that's a lot. And I'm going to do 2 more examples and post those videos today. And then you're going to have to practice this factoring process as many times as it takes to feel comfortable with it.